Hello everyone, welcome to edupediaworld.com and thanks for watching Edupedia World videos. This is Vikas Patil. This is the 7th chapter of grade 9, Intraplate Movement. This is the second session of this chapter, Earthquakes. In this session, we are going to explore how earthquakes occur and how we study and measure them. In this session, we are going to try and achieve the following objectives. Use the elastic rebound theory to explain earthquakes. Explain the working of a seismograph. Describe the different scales used to measure earthquake intensity. Compare and evaluate the two different scales used to measure earthquake intensity. Cite major earthquakes in human history. Before we begin our exploration about earthquakes, let us look at some of the common misconceptions that exist regarding the same. First, some animals can sense when the earthquake is going to come. Second, earthquakes take place only on the continents. Third, there is specific time when earthquakes take place. Earthquakes can occur anywhere on the earth. Well, this is partly true. Well, all these are myths. Let us explore the facts. As mentioned earlier, earthquakes are called master of disaster, and therefore it is very essential to understand the events that can trigger an earthquake, and even more important is to devise strategies to prevent loss due to earthquakes. I suppose we all understand that it is not humanly possible to stop an earthquake, at least not with the technology we possess currently. Earth's surface is dynamic and ever-changing. Some of these changes are very sudden and destructive, while some changes take place gradually over a long period of time. The advent of the theory of plate tectonic brought revolution in the way we looked at earthquakes. We could see specific patterns in the occurrence of earthquakes and now can easily mark locations which are prone to earthquakes. Almost all earthquakes occur at plate boundaries. All three boundary types, divergent, convergent and transform, are prone to earthquake activities. Plate tectonics causes the lithospheric plates to move. As you might imagine, having giant slabs of lithosphere moving about on a spherical shape is not smooth. We also have some places where earthquakes are experienced and they are not located exactly on tectonic plates. The reason for this is the presence of intraplate fractures called faults. The theory that explains occurrence of earthquake is elastic rebound theory. When stresses build, they first cause the rocks to bend elastically. If the stresses persist, energy continues to build on the rocks. When the stresses are greater than the internal strength of the rock snaps. Although they return to their original shape, the stresses cause the rocks to move to a new position. This movement releases the energy that was stored in the rocks, which creates an earthquake. During an earthquake, the rocks usually move several centimeters or maybe as much as few meters. The point where the rock ruptures is usually below the Earth's surface. This point of rupture is called the earthquake's focus. Just above the focus, on the land surface, is the earthquake's epicenter. It is the epicenter of an earthquake that is reported by scientists and the media. If a stretched string is broken or cut, elastic energy stored in the string during the stretching will suddenly be released and waves will appear in the broken string. Similarly, the crust of the earth can gradually store elastic stress that is released during an earthquake. From an example of the displacement of the ground surface which accomplished in 1906 earthquake in San Francisco, Henry Friel Reed, professor of geology at Johns Hopkins University, concluded that the earthquake must have involved an elastic rebound of previously stored elastic stress. In his elastic rebound theory, Reed postulated that the occurrence of faults or movement along faults is not uniform and gradual. Actually, in the interval between two earthquakes, faults are locked due to friction. During this locked phase, stresses are accumulated in the rocks adjacent to the faults due to plate movement, rising magma, or continuous deposition of sediments, till they are sufficient enough to overcome the friction holding the fault in place. The fault then slips suddenly and the deformed crust rebounds, like a broken spring, and suddenly releases the stored strain energy as seismic waves. The waves travel in all directions and cause vibrations in the earth which may last for a few seconds to a few minutes. An earthquake is therefore experienced in the form of vibrations which last for a few seconds to a few minutes. Seismic waves are produced when an earthquake takes place. Seismic waves can be of three types. They are produced at the same time, but since they behave differently within the earth, they are recorded separately. P waves or primary waves. They are also compressional waves. They vibrate parallel to the direction of movement. They travel faster than any other wave. They can travel through all mediums, solids, liquids, or gases. S waves are also called shear waves. They vibrate back and forth perpendicular to the direction of wave movement. S waves are slower than P waves, and S waves can travel only through solids. Following P waves and S waves, surface waves are also produced. Surface waves are slowest of all, but they cause maximum damage. Seismic waves such as P waves because of their great speed, the P waves are the first to reach any point on the Earth's surface, followed by S waves. By knowing the arrival time of the first P and S waves at the seismic recording station, we can calculate the distance of the epicenter from that place. Earthquakes can cause deadly ocean waves called tsunami, although tsunami can be caused by any shock to ocean water, including meteorite impact, landslide, or a nuclear explosion. When ocean water is displaced by the sharp jolt of an undersea earthquake, the seismic energy forms a set of waves. The waves travel through the sea entirely unnoticed since they have low amplitude and long wavelengths. When these waves come onto shore, they can grow to enormous height and cause tremendous destruction and loss of life. Fortunately, few undersea earthquakes generate tsunamis, while the rest are absorbed by the ocean water. The Boxing Day tsunami of December 26, 2004 was by far the deadliest of all time. The tsunami was caused by the 2004 Indian Ocean earthquake, also called the Great Sumatra-Andaman earthquake. This earthquake, with a magnitude of 9.2, was the second largest earthquake ever recorded. The energy that reached the planet's surface was 1,502 times the amount released by the atomic bomb dropped on Hiroshima. But the total amount of energy released was estimated at 550 million times Hiroshima. We use different instruments to study and measure seismic waves. A seismometer is a machine that records seismic waves. In the past, all seismometers were seismographs because they produced a graph-like representation of the seismic waves they receive. The paper record is called a seismograph. Modern seismometers record ground motion using electronic motion detectors. The data are then kept digitally on a computer. Seismographs have a pen suspended from a stationary frame, while a drum of paper rotates beneath it. The pen is weighed so that it is suspended and not attached to the ground. The drum is attached to the ground. As the earth shakes in the earthquake, the pen remains stationary, but the drum moves beneath it. This creates the squiggly lines that make up a seismograph. People have always tried to quantify the size of and damage done by earthquakes. Earlier in 20th century, earthquakes could only be described in terms of what nearby resident felt and damage was done to nearby structures. This was called Mercalli intensity scale and was developed in 1902 by an Italian seismologist, Giuseppe Mercalli. There were many problems with the Mercalli scale. What people feel and see in an earthquake is affected by how far they are from the earthquake's focus, the type of rock that lie beneath them, the construction type of the nearby building, and many other factors. Different observers will have different perceptions. For example, one might exaggerate while the other downplay the damage done. With the Mercalli scale, comparison between earthquakes are difficult to make. To address this problem, in 1935, Charles Richter developed the Richter magnitude scale. The Richter scale measures the magnitude of the largest jolt of energy released in an earthquake. Because Richter scale is logarithmic, the amplitude of the largest wave increases 10 times from one integer to the next. For example, the amplitude of the largest seismic wave of a magnitude 5 quake is 10 times that of a magnitude 4 quake and 100 times that of a magnitude 3 quake. One integer increase in magnitude roughly correlates with a 30 feet increase in the amount of energy released. A difference of two integers on a Richter scale equals to 1000-fold increase in energy. This is San Francisco, 1906, hit by an earthquake of magnitude 7.9. This was all for the session. In the next session, we will focus on the next chapter, volcanism. Don't forget to watch. Thank you.